All right, so for simplifying each of these two radicals, remember we're looking for the biggest perfect square that goes into each one. So for 32, what's the biggest perfect square that goes into 32?
16.
16, absolutely. So I rewrite it as 16 times 2, because 32 divided by 16 gives me 2. All right, now the reason why I look for the biggest perfect square, remember, is because that's the one I can take the square root of. I can take the square root of 16 and turn that into 4. The root 2, that one doesn't go down any further, so it just stays a root 2, and that is simplified. Okay, for the next one, the square root of 500. What's the biggest perfect square that goes into 500?
100.
100, yeah. And so I start by turning this into the square root of 100 times the square root of 5. And then square root of 100 is 10. Square root of 5 is the square root of 5. And so there's our simplified answer for that. So then what about these? What's the square root of a negative 36?
Solution.
There's no solution, yeah. Because if I do that, I'm trying to say what number times itself equals a negative 36, and any number times itself will either equal 0 or a positive. At least so far. That's true with most cases, but today we're actually adding something to this. Because technically I wouldn't necessarily want to write no solution for that. I would actually write no real solution. Which is one of those little details that many of you have probably wondered about. Why do I have to bother writing real? Well, today we're getting into non-real numbers. Specifically, imaginary numbers. This should go into your notes, and then we'll talk about how we can use this. All right, so you notice imaginary numbers occur when we try to take the square root of a negative. So specifically, this is going to be the most important one of those that you need to know about. That I equals the square root of a negative 1. Basically, it's kind of this basic imaginary unit that lets us then apply that imaginary number designation to any other number that we might see. Because, for instance, this square root of negative 4 here, the reason why it equals 2i is because the square root of negative 4 really is the square root of 4 times the square root of negative 1. And of course, the square root of 4 is 2, and the square root of negative 1, as we see up here, is I. So that's why that ends up equaling 2i. And you can see that we can actually use our simplifying radical rules like we were just using at the start of this lesson to do the same thing with other numbers as well, even if it doesn't work out to be a nice pretty whole. So I can break down the 12 here by looking for the biggest perfect square that goes into 12. It's just that the negative being on the inside tells me that there's going to be an I in my answer. I'll actually go through this work and we'll demonstrate how that looks here in a moment. Little side note here, this isn't a huge point of emphasis for me right now, but I do want you aware that complex numbers are then considered to be any kind of a mix of real and imaginary. Typically they look something like this, where you have something with an I in it, plus or minus something that does not have an I in it. In other words, an imaginary plus or minus a real. So going back to those same two problems that we saw earlier, let's work out how we would actually simplify these. So the square root of negative 36, of course write that down in your paper so you have the example as we go through it. The first thing I want to do is I want to break it up into two parts. I want to break it up into the square root of negative 1 times the square root of 36. That pulls the negative out. And what that does is it allows us to now deal with that root 36 like we've always dealt with it before. The negative 1 just tells me that there's going to be an I in the answer. Notice very specifically, the square root of negative 1 is I. It's a negative 1 when it's inside the square root. When I take the square root, that's where I'm representing it with I. Every now and then somebody gets that a little confused about what the negative 1 actually is or isn't, whether it's inside the root or not. And yes, it is inside the square root. All right, and then in this case, the nice part is that the square root of 36 is just 6. So it ends up just being I times 6, and just like when we deal with variables, I always want to write the letter second, so I'd actually write it as 6I. And that would be my final answer. We'd do the same process for the second one. So I'd start by writing it as the square root of -1 times the square root of 150. Then we need to simplify the root 150. And so then when I break down the root 150, the biggest perfect square that goes into 150 is 25. And 25 times 6 gives us 150. And so this is what my problem looks like at this point. Now I can go ahead and simplify the square roots that I can simplify. So the square root of -1, of course, that is I. The square root of 25, that's 5. The square root of 6, well, that's just the square root of 6. It doesn't get any better than that. And so, again, for my final answer, how do I order those three things? I do the 5 and the I first. I put the square root last still. So it's still going to be square root last. So 5I root 6 is how we want to write that final answer. Now, just as I allows us to represent numbers that are imaginary, that is, that deal with square roots of negatives, we can also find solutions that involve square roots of negatives as well. And so, please solve both of these problems. And yes, they both are now solvable. All right, now at this point in our process, this is kind of that critical point, the part where we can easily forget something if we're not careful. Something important is missing from this last line that I just wrote down. What do we need to include?
Oh, never mind. I don't have the answer.
The plus or minus. Yes, we have to remember to include plus or minus in front of the square root of the number. Because this is going to tell me that x can equal both 7 and -7. That is plus or minus 7. Because 7 squared, it equals 49. And -7 squared also equals 49. So when you take square root of both sides, remember that plus or minus. Yes, that is a critical step to remember. All right, now we repeat the same process with the other problem as well. We try to get the squared part of the equation by itself, and so I subtract the 25 from both sides. In this case, though, x squared equals a -25. But I can still proceed and take the square root of both sides. And when I take the square root of both sides, what do I need to remember to include? Plus or minus. Nothing's changed in that regard. We still have to include the plus or minus. And so that gives me an x on the left side, and it gives me plus or minus, what is the square root of a -25? It is 5I. Because remember, it's a -25, so that's why we have to have the I in there. And so our actual answer here is that x equals plus or minus 5I, or in other words, x equals 5I and -5I. And so, again, it's giving us a way to represent an answer that we never would have been able to actually represent before. Now for some fun playing with I, because I has some interesting characteristics. Now, this is just one of those things of making sure that you really understand what I is. It's going to really emphasize that fact, because if you aren't really down with what I is, these get really hard. But if you do understand what I is, they're actually not too bad at all. So for the first one, I squared, remember what I equals. What does I equal? Square root of -1, right? So this is saying the same thing as the square root of -1 squared. And what happens when we square a square root?
Rule combusts.
It cancels out the square root. And so you're just left with whatever was inside, which in this case is -1. So I squared equals -1. So I squared actually equals a number. It's no longer imaginary. I cubed. Well, a little bit of trickiness here will let us figure out what I cubed is. I can rewrite I cubed as I squared times I. It's a little bit of trickiness and creativity there. Why would I want to write it like that? Because I know what I squared is. What does I squared equal? -1. That's the one I just found. So it's going to end up giving us -1 times I. Well, and -1 times I would then equal -I. And again, the idea behind this is trying to really reinforce what does I represent. Okay, so I to the 4th. How do you suppose we'd tackle I to the 4th? I to the 4th is just I squared times I squared. And I know what I squared is, of course. I know that's -1, so it ends up being -1 times -1. And what's -1 times -1? 1. So I to the 4th ends up equaling 1. So you can see how just knowing this one piece of information here, that I squared equals -1, lets us figure that out. But again, it only equals -1 if I square it. Remember that I itself is still just the square root of -1. We can't confuse those two ideas or they're going to cause us some trouble later on. All right, last one. I to the 5th. In some ways it's really just to bend your brain just a little bit. I to the 5th. Well, I can rewrite that. You actually have a couple options here. You could write it as I squared times I squared times I. Or, I just figured out what I to the 4th was, so I'm actually going to write it as I to the 4th times I. Because I to the 4th, it worked out to be a nice pretty whole number again. It gave us just 1. So it's 1 times I. And 1 times I, of course, equals I. So I to the 5th equals I. As I said, that last one, as much as anything, is just a good brain bender to kind of make you think how unique I is. Because it really has a number of unique properties like that that you might not have necessarily thought of seeing in some other areas. So now let's put all the pieces together from today's work with yesterday's work of solving quadratics. Please solve both of these equations. So for the first one, again, we need to get the squared part by itself first. So that means, in this case, getting rid of the 7. So I have 25 equals x plus 3 squared. Now that I have the squared part by itself, I can now take the square root of both sides. When you do that, remember the plus or minus in front of the number side. So it's plus or minus square root of 25 equals square root of the other side, x plus 3 squared. The squared is still there because I still have the square root there. They do cancel each other out, though, and leave me just with the x plus 3. And then the plus or minus root 25 becomes plus or minus 5. Right, now, remember at this point, in order to get the x by itself, I do need to subtract 3, but it can be a little bit messy trying to say plus or minus 5 minus 3. And so this is a great time to split it into two equations. Make it 5 equals x plus 3 and negative 5 equals x plus 3. That way we can just do the operations on it separately. Because I still have to subtract the 3, but now I'm actually doing real numbers, just single numbers, minus 3, which makes a lot more sense. So we end up finding that 2 equals x and that negative 8 equals x. Or if you prefer a single line, x equals 2 and negative 8. Either way, state that's fine. You could list it as the two separate x equals or single line. Repeat the process with the second one. Get the squared part by itself and then square root both sides from there. All right, so as you work through this problem, we end up having to take the square root of a negative 9 in this case. So we end up with plus or minus 3i on the right side. Well, again, I need to add 5 to that. And you can split it into two equations, or because we're actually creating a complex number here, you could write it as a single line. We need to add the 5 to both sides. And you can end up with x equals, and you can either write it as 5 plus or minus 3i, which I personally prefer, or you can write it as plus or minus 3i plus 5. But notice that the I and the 5, they're not like terms, so we can't actually add them together. We can't combine them right off the top. So we actually just need to leave it like that. We leave it as a complex number for that reason.